I would like to thank the organizers for this wonderful event, and it's a pleasure to present our work here. So I am from Q Control. If you've not heard about us, we develop performance management software for quantum computers. And basically, you can think of us as we are working on improving performance of quantum computers purely through control techniques without changing the hardware. So hardware is a given to us. But there are many avenues where you can play at. So today I will talk about what can we do using QEC primitives. So this is our view of computing in quantum for next 2 decades. Some of you might think it's too optimistic, some might think it's pessimistic, but broadly the areas that you can imagine is, so x-axis is the year, y-axis is number of logical qubits and multiplied by operations. And we've just passed this break-even threshold of where various companies have demonstrated a logical memory slightly better than the physical memory. And so in some sense, we are still away from the true QEC advantage where you would want to run algorithms on QEC logical qubits. The overhead is just too much today, but with improving hardware, we'll get there. So what do we do between now to that time when it actually starts becoming useful? Because if you take a step back, think about the orders of magnitude that we're talking about. Today we are in 100 qubit realm. You get into useful fault-tolerant quantum computing, you need 10 million qubits. It was presented earlier by Masood, even by John Martinez earlier, that this is a wide, like 5 orders of magnitude chasm. And if we require us to get there and only do useful things, that's too long time to wait. So what can we do here? And there's actually quite some activity going on in the community for using QEC primitives. So you can think of it as using some partial syndrome measurements. So you can do maybe local corrections in your quantum circuit. You can think of it as error detection codes. So there's, I think, Quantinuum had iceberg codes 2 years back, and it looks like the near-term roadmap also utilizes that. Even IBM has been doing quite some work in this area, utilizing this error detections to improve performance of various state preparations or even circuits. So one of the things that is important though in all this is we need also an efficient post-processing. So let's say you get this data. It's almost like applying QEC primitive concepts from decoding into this concept here to see what can we do to do better. So most of my talk will be around some paper that we put out earlier this year. We utilize this parity checks, local parity checks, to demonstrate teleportation of a CNOT gate across 40 sites. It's one of the largest teleportation that we have seen. And also at that time, we presented the largest GHZ state prepared. It was a 75 qubit GHZ state verified through multipartite entanglement fidelity. Last month, I know that IBM actually refined these methods and also improving the hardware, were able to boost it up to 120 qubits. So it really is showing that these kind of methods are going to give us useful advantage in near future. So let's talk about the gate teleportation first. So for superconducting devices, you have, or any solid state devices, you have kind of limited connectivity. So here I show a grid. Maybe you can add some more long-range couplers, but they're still limited broadly. So here, for example, let's say you want to do a CNOT gate between this qubit all the way to that qubit. This is the connection path. So one more, like earlier, people used to think about, let's put in some swap networks. So you see there, it's a swap-based option. It takes a lot of swap gates. And if you think about the depth of the circuit, it actually goes linearly with the distance that you want to go. So the distance on the lattice from the location to the target. And this is extremely large overhead. If just to do one long range CNOT, you have to do so many swap gates, it's just give up on that as well. Actually, in 2024, Elisa Baumer showed that, well, another approach is to do a measurement way. This is something, for example, photonics people do think about. So you can think about if this kind of dynamic circuits are very hard to understand. One way to think about it is basically you're preparing bell pairs. So you can think of this as Hadamard and a CNOT. It's a bell pair, bell pair, bell pair, and then you fuse those bell pairs with additional CNOTs, and then you end up with a measurement. Based on the measurement, you can do feed forward, and then you can get essentially a long-range CNOT gate between this and this qubit. This is good in the sense that your depth of operations is quite shallow, but now you need order of n measurements. More importantly, whatever you measure here, even though you can use to correct, I mean, you know based on that measurement what, whether to do the X gate or not, it does not give you any error detection there. So there is no error detection present here. And that's why actually, I think, if I recall correctly even in that paper, this approach actually does not give much benefit over a unitary approach. So we came up with a different idea, because if you think about it, I mean, this dynamic circuit looks, at least to me, looked too complicated to intuit properly. But what did we do here? So we created this essentially a GHZ state between these two pairs, and then we projected out the qubits between the GHZ state to get essentially a long-range bell pair. So that's essentially what we do here. So if you look at this, this is one of, like, you can do GHZ state in many ways. This is one of the shortest depth circuit you can do. So you prepare a Hadamard, and now you just keep doing CNOT with the new qubits, and then your boundary keeps expanding. So let's say at this point you have the GHZ state. But one important thing we do is, once you have this GHZ state, there we were measuring out the qubits in between that you didn't care. All you need is just a long-range bell pair between these two qubits. So we actually unitarily unentangle the qubits we don't want. So by doing that, one important benefit we get through this is, sure, one of the qubits will measure out, and then that will define how to do the gate teleportation. But these other qubits which we measure, if everything is perfect, it should be in ground state. So they act like flags now. So that you can use to do error detection, to post-select based on that, and see what you can do. Now here, sure, the number of gates required would go as order of n, but more importantly, the number of measurements is, it's pretty much, you see there's one measurement here. And this is good. It depends on the system at the end of the day. So if your system has very, very small readout error, maybe you want to approach that way, and maybe make some changes in that to do error detection. But if your system has, if your gate errors are much shorter than, much smaller than readout errors, maybe this is actually a better way. So I want to also give you some more intuition. We looked at the circuits in a lot of gory details, but let's take again like one step back and think about what did we do essentially. So as I was saying earlier, you want to do a long-range CNOT, we need to generate a GHZ state, reduce it to a bell pair, and then do local operations at these edges and do measurement. And then based on that, you'll have a feed-forward thing. This was actually shown 25 years back, this kind of protocol. So it's actually a very textbook-style protocol. We made some minor improvements to this, where you can actually include this qubit as part of your GHZ state as well. That gives you a bit more boost, but broadly, this is what we are doing. And so it's actually a very simple protocol to implement on any system. And you can think of it as essentially you have a GHZ state. There are two ways you can remove, unentangle the qubits you don't want. So either just do a CNOT gate or measure in the X basis. So do a Hadamard and measure it out. So this is experimental data now. So how do these different methods work? Let's look at it experimentally. This is run on IBM machine. So x-axis is number of qubits. So you can think of it as what is the distance of number of sites that you have, what is the range of the long-range CNOT. And so the gray line is essentially the measurement approach, measurement-based approach that we talked about. It has a shallow depth of gates, but the number of measurements is very high. So this does, I would say, decent. It looks a bit low, but actually if you compare with swap-based networks, the swap-based method will just fall down very rapidly. So that's not even worth actually plotting here. But then let's say you do the unitary approach, so the entangle and disentangle approach. So you get a tiny boost here. It's a very, so including like the error bars, it's still an appreciable boost. But now you, besides just doing this unitarily, you have those extra flags. So what if we post-select based on those flags? And now you get this big boost. And this boost is coming from error detection. So essentially, if you look at from the earlier method that was known, say, 1 year back, we get like 2x boost in boosting, in teleporting CNOT. That's very promising. But then one natural question comes is, OK, you are doing this post-selection. How much are you going to throw? Is it going to be like the QEC demonstrations when 99.99% of the data is thrown out, and then it's a very nice paper figure, but it's not practical? So we measured that here, plotting discarded fraction. And it's actually not that bad. So you, at 40 sites, it's about 80% of the data is being thrown out. It's still like you're getting 1/5 of the shots. It's better than 1,000 of the shots being useful. So in some sense, I think based on what is your goal, you can play this trade-off, and you can get these benefits in near term. So now I want to transition to more GHZ states. And GHZ states are not just scientifically interesting that, oh, yeah, we created this very large multipartite entanglement state. They actually serve like quantum buses. So this was actually, I think, maybe this week, IBM put out this Loon architecture device. It looks very complicated with like long-range connections. Another approach actually also came up this year, which Bartusen and the team showed, is if you just have two planar chips, and you can use the upper chip essentially as a communication link. So actually, the GHZ approach works very well in this way, where you can now dynamically choose which qubits you want to couple in a long-range way. So here, actually, if you have good feedback with your classical control system, and also if you know, like in your circuit in compilation already, that, OK, I need this connection at this point in the circuit, you can start preparing the GHZ state in advance and basically create arbitrary such connections. One can even imagine actually taking this Loon chip and adding one more, if it was possible from fab point of view, to actually essentially get even more connectivity on demand. So for GHZ state, there is actually some more nicer things we can do. GHZ state have this very nice symmetry that you can do local parity checks, and they are stabilizers of that state. This actually is really, really powerful because then, for example, here is an explicit circuit. You prepare this GHZ state, and you do, say, a parity check. You can do like these two qubits. You just measure the ZZ between them. That should not change the state. And this actually is very nice because you can get some information about the system even with just partial check. It will not tell you all the information. It won't completely allow you to do error correction, but we can see how much will it work. So this is what we had thought, and this is, for example, the IBM device at that time. We start with qubit 57 is the initial seed, and we start growing the GHZ state. So all the green blobs you see here is the GHZ state that will be grown into. What we do is we carefully place this parity check qubits so that it's just a single, like 2 qubit gates. So there is no swap involved here. I'll also show to you towards the end what happens if you did try to do swap gates. For example, if you use this as an ancilla and try to check parity between these two, is that good or not? I'll show you in a second. But this is the approach here. And as you grow the direct size of your GHZ state, you will get more opportunities to put in this ancilla checks in between. So we verify this states that are prepared through something called MQC fidelity. This is the most stringent method you can use to be 100% sure you're not cheating to yourself in some sense, because if you just look at the population that is at half-half, that's not enough. Completely mixed state will also have half-half population. So here, one important note though here is that to check whether it's a benchmarking to verify that you did produce GHZ, you actually have to double the depth of the circuit. You basically prepare GHZ, you do some unitary single qubit layer of arbitrary rotations, and you undo the GHZ. So whatever fidelities I show you here, it's kind of the lower bound. It's not the upper bound. It's the lower bound, actually. So here we show for 27 qubits, 54, and 75 qubits. And as the size of the GHZ state becomes bigger, we have more flags we can use. So x-axis is number of flags that were used to post-select. And you can see clearly that if you are at here, you say, I don't want to use flags. This is basically what the fidelities you would get. And here we have already put in all like dynamical decoupling, error suppression, whatever you want to put in there. So you see that, okay, you would say that, fine, I have a multipartite entanglement for 27 qubits, but this is maybe on the border, but nothing here. But as we increase the information from different flags and we keep post-selecting based on that, we are seeing a clear monotonic increase. This is increasing the coherence of the state itself, essentially. Like we know which shots it did not work, and we can throw away those shots. Or if we have feedback, we can adaptively correct those shots even. So basically at 75 qubit, we showed this fidelity above 0.5. It being above 0.5 means that you can then further purify it with the purifying protocols and really get it arbitrarily as high as possible. But if it is below this line, then you have no hope to purify it all the way up. Again, let's think about how much discarding we are doing of shots based on this post-selection. And even in for the largest situation, we're like about 70%, a bit shy of 70%. So it's not 99.99% shots being thrown. I think that's the most important point here, that it's actually surprisingly low, and we are able to actually improve it a lot. And one of the things that we are able to do it such a big improvement, you might ask, well, what happened? You just checked these two parities, and why did suddenly that help you correct so many errors? And the important thing is that even though we are checking these two qubits for parity, as the circuit grows, they also have remnants or in partial information about errors on other qubits. It's in a completely entangled state. So if there are errors that happened before this qubit was reached the GHZ state, you will see the sign here. So actually measuring some places already gives you a lot of information about this. So last thing I want to show is, so I promised you I'll give you an example. What happens if instead of just doing this local parity checks, you decide, I want to get more information and do, for example, here, parity check between these two qubits. Now, physically on the device, you have to do a swap gate to do that. So let's call that type 1 style flags, and the flags that I showed before, let's call them type 0 flags. Here is the circuit for you to just think of it. Here, basically, you can do the CNOTs directly. Here, you require one extra swap gate to do it. So again, this is for say type 0 flags. You see it clearly grows. The same size of GHZ state when run with flags. Now, firstly, because you have this extra swaps, extra measurements, your base fidelity is lower. So this difference is coming just from the fact that now you have more qubits in your system. And you basically try to measure more. This is the penalty you hit. But then, more importantly, as you see these other 4 that you are seeing extra flags come in here, they are coming from type 1 flags. They help you, but the trade-off doesn't seem on this device is worth it. So basically, it's saying that if you want to think about error detection on current these devices, think about local flags more rather than having this swaps involved to get this parity information. So that's what I wanted to show about it. Now, as a final teaser of what is coming up, we are using this QEC primitives. We're working with quantum circuits team here. So we are actually, they have very interesting system where they can detect, like there is a natural flag essentially, which is erasure check. So the fact that they can do this detection, we can leverage that to get some very interesting benefits. So here is a simulated example actually using the, emulator that they have. So x-axis is circuit width, y-axis is how much improvement can we do in post-selection approach. So we have been working together to improve the post-selection algorithm itself. And here is an example that actually compared to naive approach, where all the data that I showed you before, we just throw away shorts. It's there, we throw it away. But that's very wasteful. There is still some information in the qubits or the bit strings that don't, like the qubits which don't have error there. So here you actually see, and this is, I want to caution that this is, again, simulated data, but it's showing that actually as the size of the circuit grows, you can get exponentially more yield preserved if you can do some clever data augmentation of the information that you have. So that's all I can say about it at this point, but soon we'll have some more technical details out around this. Yeah, thanks for listening.
We can do one quick question.
Yeah, thanks for the great talk. Maybe a pair of small questions. So the first is for your long-range CNOT result. Did you also compare to the unitary swap-based method and see how that performs? And then maybe a related question, did you actually use active feedback in your results, or were you just sort of post-processing it?
We did not. So at the time we ran this experiment, was in 2024, there was, I think that was not, that option was not available then. And to answer your first question, we did test the swap unitary approach. It falls off very, very fast. I don't have the data here, but I can share it with you later. So it's, I think even the just measuring immediately and the fusion approach actually does better than the swap gate approach.
With the post-processing assumption, though.
Yeah.
Because I guess one worry is like you're sort of inheriting the linear depth of the unitary method while tacking on this long feed-forward time, and so like those two together.
So actually in the measurement approach, there is no post-selection because you actually don't have information of error detection. Right. It's a feed-forward, yes. But it's a very simple feed forward in this case because it's just single gate you have to do based on that.
Yeah, thank you.